Hello, this is Dr. Sweeney, and today we're going to be talking about Boolean algebras. We're going to start out, and this is our intro to Boolean algebras. And so a Boolean algebra is a specific example of an algebra. What is an algebra? An algebra is a set of objects complete with operations on those objects, and then what we do is we construct a set of rules from those objects. So like the algebra that you saw when you were in elementary school, high school, junior high, that kind of algebra, it has the real numbers, it works on the real numbers, and it has addition and multiplication as its operations. Then what we do is we build out a whole structure just utilizing addition and multiplication and those real numbers, and what we get is we get the entirety of that basic algebra that we find. With Boolean algebras, what we're going to be doing is we're going to be using our objects are going to be zeros and ones. Zeros representing false, ones representing true. And we'll talk about that in a later lecture. And our operations that we're going to be using here are going to be addition, or the sum, the product, and the complement. And utilizing the sum, the product, and the complement, what we get is we get the entirety of all of the work for the Boolean algebra. We get all of the structure for the Boolean algebra. And so everything's going to actually build from those things. So to start out with Boolean algebra, we want to first define our set of objects or variables. And we've got this set B, and that's going to represent the domain for all of our Boolean algebra, and that's going to be 0 and 1. Now, in logic, 0 is going to be equivalent to F, and 1 is going to equal true. So 0 equals false, 1 equals true. We'll define our first operation, and this is going to be the product, which is represented by a dot, or what we might actually see is we might just actually combine x, y, or we just put the two variables right next to each other. And in the product, in our Boolean, we're going to get 0 times 0 is going to be defined as 0. 0 times 1 is going to equal 0. 1 times 0 is equal to 0. And 1 times 1, that's the only way we're going to get 1. Now in logic, the equivalent is going to be the conjunction or the and. So what we'll see here is if we replace 0 with false, we're going to get false and false. That equates to false. False and true is going to equate to false as well. True and false will equate to false. And only when we have true and true are we going to get true. And so that represents our product. And those are the definitions for a product. You can think about this as just a truth table. You're going to want to memorize those because in Boolean algebra, we're going to get some things that maybe look a little strange. Nothing too terrible, but make sure that you do have those memorized. Next up, we're going to talk about the sum. The sum, which is going to be represented by the plus, and you'll see it as like x plus y. In the Boolean, we're going to get 0 plus 0 is going to equal 0. 0 plus 1 is going to equal 1. 1 plus 0 is equal to 1. And 1 plus 1 is going to also equal 1. And so you can see that's a little strange, right? 1 plus 1 equals 1. Well, why is that the case? And that has to do with the equivalent inside of logic. In the equivalent in logic, this is going to be this inclusive OR. So we have that inclusive OR that we're going to be using. And so if you remember with your inclusive OR, false or false, that equals false. But false or true is going to give me true. True or false is going to equal true. And true or true will equal true. And so that's our logic. Now we have one more, and that's our complement. And so the complement, it's going to be represented by a bar. And we'll see it be like x bar. And so what we're going to get is that 0 complement equals 1. And 1 complement equals 0. So basically the opposite. The complement will be the opposite. And in logic, that's going to be our negation. It's our negation. So what we see is that if I have false complement, that equals true. And true complement, that equals false. And so that's our equivalence in terms of logic. What you want to make sure that you do is you actually memorize your Boolean algebras, you memorize your logic as well. If you haven't done any logic yet, that's okay. We're going to spend most of our time utilizing the Booleans inside of these lectures, but for those of you who have done some logic, this should actually be kind of helpful to kind of create an equivalency between the two and maybe give you an intuition on how Boolean algebras work. So now we're going to look at Boolean expressions. And Boolean expressions are statements made by applying Boolean variables. And those are, we call them our x's or our y's. They take values of zeros and ones. And Boolean operations, which is our sums, our products, and our complement, or the constant 0, 1. So we can actually include zeros and ones directly into our Boolean expressions. Much like, for example, when we have, like, say, 3x equals 5, we can put the 3 into the expression, and it operates as a scalar. We also have a set of an order of operations for the Boolean expressions. We'll start out with parentheses. So the parentheses are done first. And once we've done parentheses, then we know that multiplication is going to take precedence over addition. The complement is applied after all the operations underneath have been completed. So what you'll see is you'll see the complement line, but we could have an entire expression that's under the complement line. I'll show you an example of that. And then the expression is evaluated left to right if none of the other precedence rules are implemented. And so it's pretty similar to the order of operations for algebra that we've seen before. So let's take a look at some examples, see how this works. So let's say, for example, I have 0 times 1 plus 1. What you'll see here is we have 0 times 1, and that evaluates out to 0. So now we have 0 plus 1. So the multiplication comes first, then we'll add the 1, and what we get from this is we get 1. Okay, using our rules of Boolean algebra. Let's try now. Let's do 0 times, and let's do 1 plus 1. Now we've got the parentheses, which will take precedence first. So we've got 0 times, and 1 plus 1, remember, is 1. So we have 0 times 1, and that equals 0. So you can see using a different order of operations actually changes things. Let's say, for example, that I have now, we're going to take x plus y times 1. Now, x and y are variables. And so we can actually include, we can have the 0, we can have a 1, and we can actually have, or any combination of those. So let's imagine that we take, say, for example, we have 0. We'll let x equal 0 and y equal 0. And in this case, what we get is we get 0 plus 0 times 1, and that's going to equal 0 times 1, which equals 0. Or, let's say, for example, we let x equal 1 and y equal 0. Then what we get is we get 1 plus 0 times 1. That equals 1 times 1, and that equals 1. Have another shot. We got x equals 0, y equals 1. That gives me then 0 plus 1 times 1. And so that's going to be 1. 0 plus 1 is 1 times 1. And that equals 1. And then what we got is we got x equals 1, y equals 1. We'll get 1 plus 1 times 1. So that's going to be 1 times 1, and that equals 1. So that's basically how we're going to utilize our operations and how we're going to implement our order of operations to evaluate expressions or Boolean expressions. Now we want to talk a little bit about the laws of Boolean algebra. Oftentimes when we talk about the laws of Boolean algebra, the laws of logic, the laws of set theory, sometimes it gets kind of presented a little bit more difficult than it actually is. The truth is that these are basically just offshoots of our basic computation, our addition, our multiplication, and our complements. So essentially we have the base structure, and now what we have is we have some things that will actually help us to simplify our calculations. And so consequently, we want to kind of keep these in mind because they're going to help us do simplification. They're going to also allow us to create equivalencies between things that are really going to make our lives a lot easier when we're doing things like programming or building circuits. So let's start out with the first one. And the first law of Boolean algebra is called the idempotent law. And so what the idempotent law says is it says this. I have two variables. If I take x, or one variable, x times itself is going to end up equaling x, and x plus itself also equals x, which is interesting because that's very different from what we normally see in algebra. But it makes a lot of sense. For example, if I take 0 times 0, that equals 0, and 1 times 1 equals 1, just by how we've set up what a product is. If I take 0 plus 0, I get 0. And if I take 1 plus 1, I get 1. And so we can see the idempotent law holds just by testing it out over all the two different combinations that we possibly have. Next up, we have something like the associative law. And the associative law, though, is going to look very similar to what we see inside of algebra. So the associative law is going to give us x plus y plus z equals x plus y plus z, if we have y plus z inside of parentheses. Or with multiplication, it's going to be xy. If you do that multiplication first and then multiply by z, that's going to equal x times if we did yz first. Okay, you can go through and do all, in this case, 8 combinations of x, y, and z and see this is the case. But if you think about it, it makes a lot of sense. Okay, considering the fact that we're using the same sign each and every time, that should allow us to group it in the order we want. That actually is really important. Notice that the sign is the same, or the operation is the same in both cases, under both sets of parentheses. So notice we've got product here, all 3 are product, and we have all 3 are product. Over here, we had addition or sum in each case as being the same. All right, and that's really crucial for working with the associative law. Then we have the commutative law, and the commutative law is very similar to one that we see in algebra as well. Commutative means we can put it in any order that we want. So the commutative law is going to give us that x plus y equals y plus x. And xy is equal to yx. Any order that we want when it comes to working with the Booleans. It's going to give us the same value that we expect. The next one that I want to do is something called absorption. And we're actually going to utilize a table in order to show you how absorption works. The absorption law states this. It states that x plus xy is going to equal x. And then we also have x times x plus y is also going to equal x. So let's take a look at a table. We're going to construct a table, look very similar to truth tables for those of you who've seen those before. We're going to have x, we'll have y. So x will be 0, 0, we'll have 1, 1. And then we have 1, 0, 1, 0. Now you can convince yourself that those are all the 4 different combinations that we could have for x and y. Now, what we'll do is we'll figure out what xy is equal to. And then we're going to add that to x plus xy to see that we actually get the same value that we expect, that we're going to end up getting x. xy, in this case, is going to be 0. 0 times 1 is 0. 0 times 0 is 0. 1 times 1 is 1. And 0 times 1 is, and 1 times 0 is 0. Okay? Now, I'll go through and I'll take x plus xy. So x is 0, xy is 0, so 0 plus 0 is 0. I got 0 plus 0 again. X plus xy is 0. 1 plus 1 is 1. And 1 plus 0 is 1. Notice that in all cases, x equals x plus xy. So that particular absorption law holds. Going to be really important. We're going to use that a little bit later in just a minute. Now we'll take x times x plus y, and we want to see that that equals x. And so what we're going to do here is we're going to see, okay, I'm going to take my values for x and y, x plus y. So x and y. I've got 0, 0, 1, 1, and 1, 0, 1, 0. And then I'll have x plus y. And then finally, I'll have x times x plus y. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is 1. 1 plus 0 is 1. Okay, just taking these from each value for x and y. Now we multiply by x. X is 0 in this case. This ends up being 0. 0 times 0 is 0. 1 times 1 is 1. X times x plus 1. And then 1 times 1 is 1. Notice again that what we get is we get zeros and we get our ones. 0, 0, 1, 1. So what we see here is that for all values of x and y, for the values of our Boolean variable, our absorption laws hold. Now what we're going to do is we're going to do our distributive laws. And our distributive laws look different, but they look different because of the absorption laws. One of the things about Boolean algebras is since we're only using ones and zeros, and since multiplication looks a little bit different because of that, we end up with slightly different distributive laws and absorption laws and the like. So our distributive law says this. It says x plus yz equals x plus y times x plus z. Now, what we're going to do and what we're going to see is we're going to see that we're going to go through it and we're actually going to multiply like we would normally FOIL, for example, in algebra. So I'm going to get x times x plus y times x plus x times plus x times z plus y times z. So x times x, if we look up at our idempotent laws, is going to give me x. Yes, that's x. And now I've got x plus xy using the commutative law plus xz using the commutative law plus yz. Now, if I look at my absorption law, see, I get x plus xy is going to just give me x back. So I got x plus xz plus yz. And then x plus xz using the absorption law again with z instead of y, it's just a different variable, is going to give me x again. So I get x plus yz. And that, in fact, is exactly what we're looking for. And that's my distributive law. We've got a second distributive law, which is x times y plus z is going to end up equaling xy plus xz. And that actually operates just simply like you would expect multiplication to operate. This is going to be xy plus xz just by multiplying x through. And those are your distributive laws, okay? Be very careful. This is going to be one of those ones where, and we'll see some examples of this, where what we're going to need to do is we're going to need to remember that our distributive laws are somewhat different, as well as having those new absorption laws. Let's throw in a couple of others. We have some identities. We have an additive identity, and we also have a multiplicative identity. So we're going to have x plus 0 is going to equal x, and x times 1 will also equal x. So the additive identity is 0, and the multiplicative identity is 1. Pretty handy to remember those things. They'll come in handy. We also have something called a domination law. And the domination law states x plus 1 is going to equal 1. So whenever I add 1 to anything, I'm going to get 1 back. So 1 dominates additively, is what we'd say. And then x times 0 is equal to 0. So 0 dominates as well. Multiply by 0 by anything, you're going to get 0 back. Add 1 to anything, you're going to get 1 back. We have a double complement law. That is what happens when we take the complement twice. And that'll be x bar bar equals x. That is that if I take the complement of the complement, I'm going to end up with x back. Think about if I take false and I negate false and I negate it twice, I'm going to get back to false again. We have a complement law. And these are interesting. Again, these actually set up because we only have the two values, 0 and 1. So x plus x complement equals 1. Think about that for a second. Either x equals 0 or x equals 1. If x equals 0, then x complement equals 1. So consequently, what do we end up with? We end up with 0 plus 1 equals 1. Or 1 plus 0 equals 1. And that's always going to be the truth. Conversely, we end up with that 0 complement equals 1. Or we also end up with x complement is equal to 0. Because either x is 0 or x complement is 0. And because of our domination laws, these right here, it doesn't matter which one actually is 0. If the other one is 0, the multiplication is going to end up being 0 as well. And we also have that one complement is a 0. Like every other branch of discrete mathematics that we've done, we have De Morgan's laws. And what we should be able to do is recognize that these De Morgan's laws, if you've worked with logic or sets, look very similar to the De Morgan's laws that we've seen before. So for example, x plus y, what are we going to do? We're going to actually take the complement of each individually and take the product. So if we take the complement of a sum, it's going to be the product of the complement of the individual values. That's the same thing as negating and switching the sign. Okay, that's going to be that's the same basic idea. Or if we have xy complement, what happens? We're going to take the complement of each individual one and we're going to sum. And those are our De Morgan's laws. De Morgan's laws work the same no matter what. De Morgan was a lucky guy. He figured out, like, hey, this stuff works all over the place. Probably it was because he had a clever way of proving it or whatever. But the fact of the matter is I feel sometimes like, I wish I could have proven that. And those actually complete our laws of algebra. What we're going to do now is we're going to utilize these in order to kind of basically transform one expression into another expression. Basically, we're going to do some algebra. And if you remember, that's pretty much what you did for like 10 years in high school, or maybe not 10 years, like 6 years in high school. You just transformed one thing into another, into another, into another. You built more and more and more stuff out of these basic operations, and we're going to do the same thing using our laws of Boolean algebra. Now let's use the laws of Boolean logic in order to simplify. Let's take a look at this one. Let's say, for example, I have x bar plus z bar bar times x. So the first thing that I notice is that what I've got inside of the parentheses is I've got something that I can use the De Morgan's laws on. So I've got x bar bar times z bar bar. And I can multiply that by x. Then I can go and distribute. Well, actually, then I can use my double complement, and I get x times z times x. And then what I get is I get x times z, or excuse me, I can get x times z times x. Then I can switch that around. I can get x times z. And then I can use my associative law again to get x times z. Now I notice that this is going to end up being idempotent, so this ends up being x times z. And that actually is the simplification. So this, the x bar plus z bar bar times x, will actually end up just equaling xz. At each step, we can kind of see how we utilize each one of the laws. We started out with our De Morgan's laws. Then we went in and we utilized our double complement. And then what you can see is we use associative. There's our associative. Another associative here. And our commutative laws right here. Okay? I took those step by step. Normally when you're simplifying, you probably would just, kind of flip everything around knowing that you have associative and commutative laws. All right? But you can see that this actually could make some of our statements a lot easier. Some of our expressions a lot easier to go out and figure. Let me show you a couple little tricks here. Let's say, for example, I have x plus xy. Remember, we use this, and this is one of our identities. We want to show that this actually equals x. All right? So we're going to use this now in order to do some proof. And I want to kind of simplify the whole process of proof. All this process of proof is basically it's doing some algebra here on the Boolean algebras. So we got a little trick here. We're going to take x times 1 plus x times y. Okay, we know x times 1 is equal to x because of our identity laws. Or we could just write this is identity. See how that's the case. And then I also have, I'm going to now take that and I'm going to go distribute. So I'm getting x times 1 plus y. Okay, and there's distribution. And now what I've got here is I've got x times 1 because 1 plus y is simply going to end up being 1 by our domination law. Finally, that'll give me x, and it's x because of the identity law, because anything times 1 is going to necessarily be equal to 1. And there we go. So what we can see here is this is just a simplification as well. What we did, we had a little trick. We multiplied by x times 1 and then x times y, and that allowed me then to go through and distribute, or basically to factor. I'll factor out the x. And then 1 plus y, that's going to always equal 1. Anything that we add 1 to is going to end up being 1. That's my domination. And then when I multiply anything by 1, it's going to give me back the value as well, and that's identity. And we're done. And that actually is a proof. Basically, the ideas of proof and the ideas of simplification when we're working with Boolean algebras are essentially the same. And oftentimes, we're just going to do the simplification, and we just want to do the proof as a learning tool in order to kind of make explicit what sorts of processes that we're doing in order to do the simplification. So in this mini lecture, what we've done is we've gone through and we've discussed, one, the basic structure of a Boolean algebra. We've discussed its different operations, which in our case is going to be addition, the product, and the complement. We've shown how it is that we can go through and evaluate those expressions, how we utilize those order of operations. And we've also shown some of the laws of Boolean algebra and how we utilize those in order to simplify. Some things that I really think you should do is make sure that you go in and you memorize the tables for the product, the sum, and the complement for Boolean algebras. That's actually going to help you out quite a lot. You also want to make sure that you've done a little bit of practice with simplification with Boolean algebras, because that'll actually make things a lot easier when you start working in things like functions for Boolean algebra. Note that really all we're looking at is we're looking at a simpler kind of algebra than we saw, say for example, that you saw inside of high school, or early on inside of calculus. We're looking at a system that actually only has two inputs, and because we only have those two inputs, we're somewhat limited in what we can do, but also we can expand that quite significantly because of the kind of the versatility of our functions and our operations. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.